So today we are very happy because we have Professor Cynthia Ebinger from the Department of Earth and Environmental Sciences at Tulane University, who accepted to give us a seminar. So we thank you on behalf of everyone. We thank you very much. And she's going to talk about the consequences of magmatic activity on the lithosphere with example from East Africa. So Cynthia, the floor is yours.
Well, thank you. I feel I'm very flattered to be presenting. And I guess what I thought would be most helpful for many of you students in the group is to have a perspective on how we got where we are now, and in terms of lithospheric deformation models, crust and mantle lithosphere, and eventually how we then couple them with the dynamic mantle. And I guess I think when I teach classes, I see that students' eyes glaze over a little when they think of all the different processes that are occurring and how we're going to come up with a model that is rigorous and explains the physics of the problem, and how we take this apart step by step. And first, historically, with analytical models in 1D or 2D. And as time has gone on, then numerical models that are tested and calibrated in general against analytical models. And then as we move, in a way, how we can look at increasingly more complex numerical simulations and design tests and calibrations, both against data and against semi-analytical models as well. So I'm not going to get into the model part, but I'm somebody who's pretty invested or invest in data and in observational sciences as well, and working with primarily crustal seismology and working closely with mantle imaging as well. What I also want to do today is give a background and then give a case study that features Sarah J. Oliva, who is a ICTP diploma student. She was a PhD student with me, and she's now a postdoc at the University of Victoria in British Columbia, working on transform fault processes as well. But I think that her work, it gives a really nice illustration of how we put these pieces together. So let me move forward here. Maybe. There we go. Sorry. So let's just look in general at what is happening in a rift zone. And unlike a subduction setting, the plate, well, I'm generalizing, of course, but an important part of the process in an extensional province is that the lithospheric properties are changing over time. So not only is the plate thinning, so our compositional boundaries are evolving over time, but we're transferring heat, and we're not transferring heat in a simple way, particularly in the case if we have magmatism within the system. So let's just look at our plate and think about boundary conditions. What is important in this situation? We have a crust. For simplicity, let's just give it a bulk density of rho C. We have a mantle, give it a bulk density of rho M, and an asthenosphere underneath that's slightly less dense than the mantle, just slightly. So this would be our normal piece of lithosphere before stretching, and over here is the most extreme case then of stretching in the case. If we look at the rift, in this part of the rift where we have a basin, like the Kivu Rift Basin, we have replaced crust with air, water, and sediments. You can see that, here's this horizontal line of where the crust would have been, and we may have sediments and water that replace them. Those are less dense than what had been there. Down at the bottom of the plate, we have replaced crust with mantle that is more dense. And that gives it, if you think about balancing this, isostatically balancing this column with this, then that's going to pull down. We also have uplifted rift lengths. And I immediately, and I'm going to go into this in a little bit later. Some of the original models for continental rifting assume that plates are weak in extension and we don't have to worry about plate strength, but we're going to look at that in a minute and say, no, that's not the case at all. But let's, underneath here, this is the zone of mantle dynamics. And as the upwelling mantle rises, particularly if it's hotter than the surrounding area, or maybe more volatile rich, we may have some decompression melting, and I'll talk about that in a second. But with the melt production, there's also volatile release, and that's primarily in a continental setting or a cratonic continental setting. That would be CO2 plus water, and that water is available to interact and CO2 to interact and form new, or what we call metasomize the lower part of the mantle lithosphere. So I'm going to talk you through these pieces and start to think about what's changing in the system, where there are what we call body forces or acting across the whole system, and whether they're horizontal and vertical, and how they will then change the shapes of the basins over time. And then what happens later on, then we're going to jump in and add some magma. Now, this is a 2D problem that I'm putting in front of you. Rifts are very definitely 3D, and they are segmented along their length. And so already it's an oversimplification, but we have to start somewhere. So this is where we'd start in the problem. In some cases, we know that there are volatiles and large amounts of volatiles rising upward, because we actually can measure those volatiles, not just coming up at volcanoes, but coming up along fault systems. Okay, so, the simplest case, we take a simple mechanical model. Here's our crust, there's our subcrustal mantle lithosphere. There's a asthenosphere underneath. This is what it looked like before. It had a thickness. In East Africa, it might be 150 kilometers. Oh, then we stretch it. Let's just stretch it instantaneously. Let's just pull on it and create a basin at the surface through a necking process. Here's our mantle that's now filling what used to be crust. Here we have some low density material, water or sediments in this area here. Well, that's a mechanical model, but that doesn't take into account isostasy. So we can, using geometry, and we can also take, use a thermal model like those developed for the creation of oceanic lithosphere to predict the temperature versus time in a rift zone. So let's go ahead. So let's just look at this profile. This is our normal piece of lithosphere. This is depth on the vertical axis going down to 150 kilometers, the base of the plate. And the base of the plate then is a conductive profile. And in the mantle, we have an adiabatic geotherm. So it increases just slightly related because we have this well-mixed convecting mantle. If we stretch the lithosphere by 50%, and now it's 75 kilometers thick, we now have 1350 at a depth of 75 kilometers, and we can compare these two profiles, and we see that the area between the two of them is effectively the heat that we transferred to the plate. So yes, in geology, the plate, or in geological time, the plate is not going to stretch instantaneously, and there's a finite time period. And so this is a slightly overly simplistic model, but in a numerical stipulation, we would take a time step and then increment the geotherm over that time period. So we're not calculating it every second, or we may be doing it every 1,000 years or every 10,000 years in this sequence. And then if we stop rifting, that heat that was put into the plate, maybe 20, 40, 60, 80, 100 million years afterward, will continue to be lost. And so the plate will cool, and the plate then has to continue to subside after we heated it during these early stages. So So there are many papers since the late 70s, and we have a good, yes, we can predict T of Z and T over time, and you may have done this as an exercise in a class. Well, changing the temperature will change the density. And these are relatively small amounts, but we can't neglect them because the mantle lithosphere might be 100 kilometers thick. If we have a 150 kilometer thick plate, a 40 kilometer thick crust, we've got 110 kilometers of mantle. So a small change over that kind of thickness then could lead to some significant forces on the plate. So we have to, so we start with the thermal and breaking down this problem in that way. Okay, so now we can predict what the temperature versus depth is and what density versus depth would be. But then now we want to then consider then the isostatic adjustments for this. And can we assume area isostasy? No, bad move. Because if we were to do that, we would only have isostatic adjustment for the replacement of crust with lighter material that gives you a net upward effect. And this crustal thinning and the mantle replacement for the crust, a net downward, there's usually a net positive or uplift related signal, but it would only be accumulated in the area of the basin if the plate had no strength. Every little bit of compensation happens in vertical columns that would move relative to one another, and which is really not an appropriate way to look at rifts. And we've known this for 20 years, more than 20 years, almost 30 years actually, whoops. So the presence of these uplifted rift flanks is then an indication of the need to consider plate strength. So now we're going to go into the big, what we call a chestnut, or the major problem in plate tectonic. One of the two big ones. One has to do with the viscosity of the upper mantle, and the other has to do with what the composition and rheology of the crust, primarily the crust, is in a very heterogeneous continental lithosphere, of lithosphere spanning Archean to modern ages. So this is where we run into problems. Now, for right now, ignore the magmatism. We're not thinking about magmatism in this problem. Okay, so what do we know about rift basins? We know actually a lot from actively deforming basins. This is maybe a bit of an end member this is the Tanganyika rift, where we have Proterozoic lithosphere that's fairly thick between two cratons. The amount of stretching or thinning is very small. The amount of heating is relatively small as well. And the lithosphere is apparently quite strong, because here on this profile, let's just take a look. We have a basin. These are two profiles across the southern Tanganyika rift. We have earthquakes in the lower crust. So we know the thickness of the crust roughly from receiver function analyses. We can see that earthquakes are along projections of faults that have been well imaged in seismic reflection profiles and imaged, and their faults then are observed on land. This is a vertically exaggerated profile. This is 1-to-1, and you can see the uplifted rift flanks of the basin, and the basins are strongly half-graben, meaning they're asymmetric. One big fault on one side of the basin seems to accommodate most of the crustal extension in a brittle manner across the basin. And in this case, you'd say as well that, well, if you have earthquakes in the lower crust, then the entire crust may be brittle. If you look at this one, where we also have focal mechanisms, they are, the nodal planes are along projections of the border fault to depth as well. There may even be some earthquakes right in the upper mantle. And interestingly, here is a suture zone between two orogenic belts, and and there may be some earthquakes associated with that zone. So in this case, we have broad uplifted flanks, a crust that's strong throughout its length and its depth extent. And the border faults or the fault systems in the basin are about 100, maybe 120 kilometers long. And civil engineers and know full well that the length of a fracture scales as the thickness of the strong layer, and even in a layered material. And so these fault systems are indicative of strong lithosphere. So what happens when we extend strong lithosphere? Let's take a look. Okay, so let's just, I don't know how much any of you the students in the course have done on crust and mantle rheology, but a review is always good. So let me just bore some people and give a bit of a review for others. And let's just define the strength of a material as its shear stress at failure. So that is a good explanation. We have to consider the cohesive strength of a material. That's the little friction between particles holding them together. And so we can describe this in a way where we can describe the strength, that's the cohesive strength, then plus an applied force and the internal angle of friction for any given material. So those are rocks. Those are the rocks comprising the crust. And we end up with a lot of laboratory material experiments with a range of crustal rocks, gives us approximately 0.85 for phi, our internal angle of friction. It varies a little, but not a huge amount. So we end up with a relation that's something like 0.85 times the stress. And since the stress is in most cases lithostatic, or the applied pressure that we consider in the situation, that's density times gravity times depth, that gives us a way to approximate the shear strength, the strength of a material. And this is from a relatively recent review paper by Bergman and Drayson. I think it's a really nice way to try and introduce the yield stress envelope. So that relation that I just told you there, or the failure, is called Byerly's law, another way, and that's here in this case, that's this line here. Okay, do you see this line coming from zero and extending down through? Here's our crust, and in this case, the crust is 30 kilometers thick, and it comprises an upper layer of quartz and a lower layer of feldspar, and it's hydrated. So there's a small amount of water in this material. And so you see, do you see this line here and this line here? Well, these are dislocation creep curves with a strain rate, assuming a strain rate of 10 to the minus 14 per second. So we superpose this brittle envelope and the ductile envelope, and the area under the curve then is the strength, or the yield stress. Here we have a dry olivine in the mantle. You see here's this yield stress, and then the intersection with the dislocation creep. Now, these little pictures underneath here are current ideas for what continental plates are. Do we have a jelly sandwich? So we have kind of strong with weak stuff in between, and then strong, and they're maybe even the jelly might even allow them to be decoupled in some situations. And of course, these curves, by the way, are dependent on the geothermal gradient. So that's why we always consider the geothermal gradient first, so that we can find the appropriate conditions for the rock compositions that are appropriate also for any given area. If we go here, this is called the creme brulee model, where we have a strong crust and a weak mantle underneath, where it's deforming almost exclusively by diffusion creep. So that yeah. Anyway, within the crystal lattice structure, then the material is diffusing. So, and then the final one is like banana split, where the plate is weak and wet, and gooey, and there might be some strong bits within it, but not much else. And throughout, the mantle is so weak that it's undergoing diffusion creep, and which is a slightly different process. And let me just quickly, I know I do want to get into the details and lose sight of the forest, get lost in the forest, but just to say that the ductile deformation has a time dependency, and there are physical properties that we have to consider. It's a power law relationship. There are the two exponents n and m that are dependent on the different materials and the different geothermal gradients. There's an activation energy, but there different materials can, depending on their grain size, move from diffusion creep to dislocation creep at over different temperature ranges. So this is what we know by squeezing rocks in the laboratory and finding out how they behave and how they deform. This would be wet quartz and wet plagioclase. This gives us then a predictive tool to then put into a numerical simulation of lithospheric rheology. So this is how we get to these big models with an awful lot of knobs that we can turn, but they've come from these rigorous studies that integrate rock mechanics information and put them together in a realistic, or as realistic as possible, way to simulate the lithosphere undergoing extension with changing thermal conditions and then consequently densities and physical strength properties. And then the difference in diffusion to dislocation and diffusion creep. Okay, so anyway, let's just kind of summarize all of this, that continental plates retain significant strength and extension. So we're going to have to consider the rheology, or the time-dependent behavior of those materials. So we're going to include flexural isostasy and our isostatic balance. So what we're going to do is just say that column A before rifting equals column B after rifting down to the base of the plate, where both sides are in the asthenosphere. And this way then what we can do is quantify lateral density variations within the plate that lead to both buoyancy forces, or up or down directed forces, and also these lateral pressure gradients then can enhance extensional forces pulling apart the plate, or in the case of the thinning, the replacing the lower crust with mantle, then that would counter extension and lead to a slight compressive force because we put something more dense in. So the lateral pressure gradient then leads to a net compression. And that's, so these are things that we have to consider then if we want to understand how rifting progresses over time. And as I think you all have been taught by Professor Eleonora Revolta, who always says, reminds students and says, know your stresses. And this is a part of the process that we want to consider. And I'm just, for what I'm talking about today, I'm just ignoring sublithospheric convection and advection processes. Those dynamic processes. I will, in the case study I'm going to give you, I'll mention those, but I haven't taught you anything about that. So I hope that some other lecturers and others will present to you about some of those processes and how that we link dynamics, or the complex process of linking dynamics, mantle dynamics, to lithosphere and transfer stress with this big chestnut of what is the how variable is the viscosity of the uppermost asthenosphere. Okay, so rift flank uplift. Let me talk you through a diagram. This is a classic diagram, and I think it really tells the case that if I stretch the plate along a fault, and maybe that fault goes all the way through the lithosphere, let's just create a geometry of thinning, where here's a plate, there's a fault system. I drop the crust down, and in this part of the model, I have replaced the crust with air. I've changed the density down here, and I'll have isostatic restoring forces. Well, in the case of no strength of the lithosphere, that's this dashed line. I balance column A with column B. I look at my net uplift, and I get a basin depth of about 1 kilometer. And all of the subsidence occurs in the basin, and there's no, the basin subsidence has the isostatic adjustment lifts the basement a little bit. And this is what we get. We predict a 1 kilometer deep basin. Well, if the plate has strength and an equivalent strength of a 5 kilometer thick uniform plate, that would be this line right here, where you see we have a 1.5 kilometer high uplifted flank, and we have a basin now that's 2 kilometers deep and a half-graben. As we increase the strength of the plate, the breadth of the uplifted flank increases and the height of the uplifted flank does. The maximum basin depth doesn't increase by a great deal, but the width of the basin increases with strength as well. Because you can think about it, if you take one sheet of paper and you bend it, it's fairly easy to do. So that's a weak plate. But if you take 50 sheets of paper and it's going to take more force, and they're going to bend with a larger or broader cone. So this is the critical part, or a critical part of our way to match our models with observations is to match the morphologies of the basins, and also these morphologies over time. So we can see patterns at the surface that may look like fault patterns. But by also looking at the isostatic compensation or the predictions and matching those to time-dependent topography and basin depths, basin geometries, we can start to eliminate plausible models and reduce them then to a small number and really dig into the physics of a process. And these are the isostatic restoring forces that we've replaced crust with mantle, and you can see then that there's a step associated with the replacement of, or the crust and mantle displacement down in this part. And it's these forces then that we're talking about. And because the plate has strength, the isostatic restoring stress here is going to be shared with the plate way off here and way over in this direction, because they're a cohesive plate that's going to be bending. So I hope that you understand where I am right now. So we can now calculate and predict topography, basin morphology, rift flank uplift over time and over our time steps in a basin history to try and match then the observations that we have for flank and basin uplift and subsidence, which are observables that we have in most places. Okay, so the last piece of this that I want to get into is just to try and help you understand how, in a simple way, there's considerably more to this, but as a starter, how we then put magma into the system. So we have a crust and a mantle, okay? In this, over on the left-hand side, and if we think in this case, this row S, we're just saying that this is the simplest relationship over here. So we have two layers that'll have to be done, break this integral down. But here's our crust, it's got a row C. Here's our mantle, it's got a row M. And here's our magma that has a density rho F, or you can say it's a fluid pressure within, or fluid density within that column. That material is much less dense than the mantle, and it may be equivalent or even less density than the crust. So it has a buoyancy force. And we can think about that in terms of the pressure gradients within. Here on the left is the line for a fluid-filled crack that rises to the surface. So here's and we can look at the differential stress between the two of them. This is depth here, and this line is the fluid pressure within that dike. So this magma, Yeah. Let me step back really fast. As we thin the lithosphere, we bring mantle up. And when that mantle is depressurized at depths equivalent of about 80 kilometers subsurface, we start to generate a few percentage melt and volatiles may escape. That might happen deeper if it's hotter, but just saying that we've crossing the liquidus solidus boundary, or the solidus to the liquidus, and we generate melt. Once that melt is available in a system, it has a buoyancy force. And that buoyancy force then increases into the mantle. And this blue hashed area then is the force available to add to the tectonic stress. And if you just look up in this diagram here, we go back to our yield stress envelope. This is our Byerly's law, and there's the strength of the crust and the mantle. But to cause a fault to slip here, I'd have to achieve yield stress. Whereas I can put a dike into the mantle at a very small percentage, almost 1/8 to 1/10 the amount of force required to cause slip along a fault system in here. So diking, because or magma intrusion adds to the tectonic stress, and it can explain then, if we look at the forces available, this would be a ridge push force, tectonic force, and magmatic, that at different lithospheric thicknesses, we can start cramming magma in to the plate. Well, what happens, the width of that dike that is intruded is extension. The plate is being stretched apart in effect by the width of that dike as well. So it's achieving the process of plate extension, and we have these buoyancy forces. So what we can, thinking about this is a really useful tool, and I'm going to come back to diagrams like this when I give examples from Sarah J. Oliva's work. Okay, so let me just review really quickly, and why you can look at the draft because maybe it's more fun than I've been talking a lot of words. Plates heat during thinning, and that causes density changes. If we have, if the temperature at the base of the plate, or the rising asthenosphere gets above the solidus, or even the base of the subcontinental lithosphere, then we can generate some melt. Well, if there's melt, then it has a buoyancy force that wants to rise upward, and that magma will also transfer heat to the rocks locally. And so that may enhance the amount of heating, and we may start to get hotter zones within that zone of stretching. The plate strength is going to reduce because the yield stress, or that our failure relation, Byerly's law, is temperature dependent, or geothermal gradient. The hotter it is, the weaker the material. Okay, and then if we generate magma, we're going to release volatiles that can percolate up through cracks and have metamorphic reactions. And those metamorphic reactions will reduce the strength. Okay, so let me just now set up what I'm going to do for the last part of the talk, and I'm going to give examples. So this is not Oliva, this is Olive, Jonathan Olive, from a GRL paper that is just considering the crust, but looking at the challenge that numerical simulations of extension face when we set up using an engineering type model where we assign physical properties to the plate, we apply stresses, and then look to see where failure occurs. It's hard to maintain or create a half-graben basin, yet we know from areas in East Africa that the same half-graben basin has persisted for 10 million years. And one of the ideas that is out in the literature is that maybe if we have a lot of erosion and change the shape of the flank, that it can help localize or maintain the strain along one fault system, rather than having strain jump, say this would have been a fault system here, and then strain localizes to a new area at time 2, or in this different types of models, we can see that we can have at time 1 a fault system, time 2, time 3, different geometries and different basin shapes depending on strain rates and physical properties. So, the lower crust is a big question mark. What is the rheology of the lower crust and what can we say about it? So my attitude and my approach and my research group has been looking at the role of or using low earthquakes in the lower crust to help us understand the physical properties of the lower crust in extension. And we also have been looking at areas that have crustal xenoliths, so volcanoes that blast up pieces of the lower crust that let us know what the hydration state and composition of the lower crust is as well. So that's so this is what we're going to look at a basin, and we're going to look at 2D and 3D. Okay, so where am I? All right, now finally, relax. We're in East Africa again. Well, many of you are in East Africa. Atala is up here, and some of you are watching over here in Kigali. So I'm going to talk about an area here. So the East African Rift System involves the Red Sea and the Gulf of Aden, and they're associated with Arabian Peninsula being pulled off with the closure of the Tethys Sea. There's subduction occurring then in Zagros and the areas up to the north. And so that all started 30 million years ago, and those rifts have a different orientation. Part of the IIFR was created about that point as well. But this area south of there has developed since about 25 million years ago. And all of these black lines and volcanoes, the red triangles are Holocene volcanoes, and then there's some orange ones that are Pleistocene volcanoes. So there are a lot of volcanoes in some areas. There are volcanoes down in through here, and there are a lot of cratons. And the cratons have much thicker lithosphere than the surrounding orogenic belts. And then also too, within these areas, you can see some green lines. These are areas that were rifted during Mesozoic time. They have thinner crust, and they may have been a little bit hotter when East African rifting started. So let's go down. So this is where my team is, or I'm working with a big international group, including Professor Atala Ayeli. But where I'm going to show you what's happening at the edge of a craton down here and around the volcanoes, including Oldonyo Lengai, the world's only carbonatitic volcano that's active today. Okay, so the rifting is occurring above mantle plumes. And I don't know what just happened to that title. It should just say rifting above mantle plumes. But this is from Alistair Boyce's recent papers. This is a depth of 1,300 kilometers, 1619, 2,300 kilometers. So we're below the mantle transition zone, and we're looking at velocity anomalies relative to model AK135. And these changes in P wave velocity are plus or minus about 1%. You can see the scale down here, 1% red, positive 1% blue. And there's at 13 to 16, it looks like there's a southwestward dipping area underneath B that goes further to the south underneath South Africa when we get deep in the mantle and go down to the core mantle boundary. So rising from the core mantle boundary to the base of the lithosphere, and I don't have those here, but we know that it rises up in through this general area. And these are deeply rooted mantle plumes. And there may be another one, or it's probably another one over to the east, rising from the core mantle boundary, this A, and it's tilted a little bit towards the west. Okay, so we have rifting above mantle plumes. All right, this rift is less than 7 million years old, and from extensive seismic imaging studies over the past several decades, we know from 2D and 3D imaging that there's about 20% new igneous crust. So magma has been generated below in the asthenosphere, risen through the mantle lithosphere and up into the crust. And we know reasonably well where it lies. These are locations of refraction lines and all the seismometers that have been stuck in the ground throughout this area. These are MT profiles in purple here, and just in general, this is where we're looking in East Africa. This is a mantle, a joint inversion of density and P-wave velocity by Christel Tiberi and others, published in 2019. And what you can see is thick lithosphere on either side, and then areas with lower density, lower velocity material in a narrow zone that's about 100 to 150 kilometers wide. And there's the possibility that there's actually been lateral erosion of the craton over the past less than 10 million years. Along this very steep edge, and the lithospheric thickness beneath the edge of the craton might be 150 to 170 kilometers. Prior to rifting, there are some kimberlites that say it was probably 170 kilometers thick prior to rifting. In a recent paper by Muirhead, I told you I'd say something about these volatiles. Well, and magma, we generate magma, but the volatiles kind of get their way in and crack their way in. They can do things like the olivine-rich materials can be turned to dolomite. It's a rock that's like a carbonate, and it's soft. So we take something that's really strong and we can make it soft by adding CO2 and looking at these reactions. And those reactions then release water that percolates upward and makes other minerals softer and weaker as well. And it's possible that the base of the plate, with the introduction of volatiles, can get stripped off. It can actually move laterally and downward out of the system. And so maybe what's coming up in the rift, both in terms of magma and gases, may have moved laterally away from the edge of the craton and upward. And this is a numerical simulation from Craven and Van Wyk showing how that process could work. If you have a steep edge and buoyant material, some of the material can move sideways, as you see here. You see some green material moving this way and then could come up in the rift. So maybe these things are happening in our rift zones, and maybe that's why we're seeing lots of CO2 degassing to the atmosphere in rifts. I'm not going to say very much about this. Just I put this in here just to say that there's a lot of seismic imaging that's been done. These are crustal velocity anomalies. These are VP. Variations in VP in the crust, and then all these dots are earthquakes, and the earthquakes happen along the edges of bodies. This is imaged as a lower crustal magma intrusion, magma body. This is a blow up of this box up through here, and then there are in plan form some patches of seismicity, and they're associated with the dike intrusion, and we interpret them as sills above the magma body. And anyway, we're seeing rapid intrusion of magma into the crust over time. We can even get some crude estimates that rates of crustal accretion here, new crustal material added, are the similar into subduction zone volcanic arcs. So let's talk about ICTP alum Sarah J. Oliva. So she's looked at, these are a couple of papers, I'll leave these in here for you, but she's also looked at this area in terms of full moment tensors and found non-CLBD source mechanisms associated with faults above sills, and is adding some new information on magmatic rift zones. Right here, she's making soil gas measurements to contribute to the studies of CO2 degassing. And that's Oldonia Langai in the background. So what she, in an EPSL paper in 2022, she built an analytical and numerical models to study the role of surface topography. She's going to go through all those steps that I just talked about at the beginning, where she takes a model where she has topography. So topography gives us gravitational potential energy. We have relief. So we have different pressure gradients in different areas, depending on how high the rift flanks are and how deep the basin is. We have, in this case, we're going to assume a uniform crustal composition, but we know the upper crust and lower crust because there are xenoliths of the lower crust. And we know it's granulite that's only slightly hydrated. We know the mantle, and so she's assumed a mantle lithosphere here, and we can see the cross sections. And then this is where we image the crustal magma body and the sills above. And this is an area where a dike was intruded in 2007 within the area. And why is she looking at this? Well, what she's trying to understand is why the rift opening direction, which is almost east-west, a little bit northwest, northeast. So up here, the rift extension direction is like this. In this area with a lot of volcanoes, it rotates to northwest, southeast, and then goes back to east-west down here. So what's different about this area, and how can we have a local rotation in stress direction? Is it caused by the presence of magma bodies? And what role does the zone of crustal thinning have to do? Because I've got density gradients down here at the base of the crust. So Sarah did analytical and numerical simulations and took it apart and said, okay, how does the vertical stress and the horizontal stress change with just topography? Green line. Oh, look at the horizontal stresses that are created by having lateral variations in topography. Okay, what about a magma chamber in the lower crust? Oh, that has an important effect in both the causing vertical changes and causing horizontal changes. What about the moho, the shape of the lithospheric thin or the crustal thinning in the area? Well, that has a significant impact as well. And when we sum all of them together, you can see the net effect here is this blue line. And then, so each of the different components that we were talking about earlier, then we can address in the way that we look at horizontal and vertical stresses, and then can look to see what's driving models. On the right-hand side, you can see Sarah compared her observations with the depth distribution of earthquakes from monitoring in this area. And you can see that the majority of earthquakes are occurring in the upper 15 kilometers in this area. And that's partly in the area where we have the silt complexes as well. And it's associated in part then, they're gonna, what we see in terms of stress is gonna be dominated. Those earthquake focal mechanisms we were looking at are coming from this depth. And if we look at the stress changes in these areas, it kind of makes sense. Okay, and so if we put these together into a 3D diagram, this is that same area. These are inactive volcanoes. Oldonia Langai is lying right about there. And then we have a shield volcano, another shield volcano. And these are the stress directions and projected onto a horizontal plane. And over here, this is the GPS opening direction, the teleseismic t-axis, and then the local focal mechanism t-axis in this box only. The GPS are from outside the box, so it's a little bit misleading. So there's east-west direction from geodetic data. But if we look at just topography, doesn't explain the green arrows. They don't match. Well, the green arrows from topography match the GPS. But if we want to explain the earthquake focal mechanisms, we need to take all those components and pull on the plate out of tectonic stretching. And then we can get these green arrows that match the observations of earthquake mechanisms from earthquakes that occur in the upper 12 to 15 kilometers of the crust. So putting these pieces together, then we end up with a model that says that these components, the lower crustal magma chamber and dikes and sills, not only are controlled by the stress field, so where they intrude is determined by what the stresses were when the magma is rising, but they then locally perturb the stress field and will guide subsequent magma intrusion. So once we start putting magma into the system, we need to be aware of both the crustal thinning and the distribution of magma within the crust if we want to predict the way the stress field is evolving over time within a rift zone. And we want to be able to predict about the stress field over time because, whoa, magma storage in the crust, well, surface eruptions may be only 1/3 of the magma volume. We may have, if you have an eruptive flow, there might be 3 to 5 times as much stored within the crust. And that material could move somewhere else or cause a dike intrusion or fracturing that would be very harmful to people living above those zones. So that intrusions are hidden hazards in volcano zones, and they're also potential sources of geothermal energy. So they're very important to us. And I'll just leave, at the end with a comment that in 2021, there was an eruption at Nyiragongo, and there were also migrating swarms of earthquakes interpreted as dikes, and in the zone, so the dike may have been here, but faults form above the top of the dike if they don't reach the surface. And these are some of those faults that hit the town of Gisenyi in northern Rwanda, with big open fissures and fractures that no building can withstand those kinds of dilatational strains. So this was photos taken by Derek Morchese, who's a Georgia Tech PhD student. Okay, so just to say at the end, we're working in this area of northern Uganda and so southern Ethiopia, and what did I say, at the Uganda border and in northern Kenya. And we've got some exciting results. Some things are already out. Kunudis et al. and T-Cube did another paper by Ogden et al. And a lot of the state of stress and work on seismicity is in progress, and hoping to have that submitted by the end of the summer. So I just go backward then and just leave you with this slide and say thank you very much for your time.
Well, thank you very much, Cynthia, for this engaging talk. I'm going to ask if anyone has some questions. There is one already in the chat. Cindy, how do you calculate the effect of intrusions in the model? Is the model compressible? Do you only consider the thermal effects, or do you have a compressible model?
So it's a static, Marta, I didn't explain, and I should, that this is a static model, and no, that it was, let's see, the pilot is not well suited to consider compressible fluids. So there were analytical simulations and approximations made in modifying pilots to be able to do this. So Charles Williams and Sarah worked up an approximation for this within pilot. But in this case, we were just trying to look at the static problem as a starting point and saying it's really hard to move back. Did that answer your question?
No,
she's still asking.
Sorry,
Yeah, exactly.
It's a static problem, but when you do the static problem, then you were looking at the thermal contribution to the stress field or the density contribution of the magma intrusion.
The density contribution.
Okay.
Yeah.
There is a question by Yang Wu Xu. Go ahead, you can ask your question.
Great. Cindy, hi Cindy. It's
Hi.
Nice presentation. I really appreciate your summary for the geodynamic models and the equations. And my question is also related to the pilot static model. So I can totally understand there's we have to do like using static models, and this is confirmed that there's no thermal effect and the melting here, right? And also,
No, and what we were cognizant of is that Joe Dufek is involved in another project in this area with Toby Fisher and James Muirhead, and he has been modifying melt to consider the to simulate, so that Sarah was going, when that has is a bit better advanced, then that's the next step to consider, is to actually incorporate, because right now MELTS does not consider alkali basalt melting, and it's not, the numbers are not, yeah, well, they're very, let's just say, they're guesses. So in trying, and it can't match the CO2 as well. So in trying to do this better, we're waiting for better simulations from Joe. But that is definitely on the radar, and something that we view as really important.
Yes, thank you. And also for other like topographies and thinning of crust is, I think it's easier to constrain in the static model pilots. But for the magma chamber, so the inflation of the magma chamber, how fast is it? How do you constrain that?
We're not, because it's static, we just don't, the realization of what to do next is big, and start with something that, for any PhD student, I would always say, start with something where you build confidence and you have a very strong platform, and that's where she started. So yeah, don't jump too quickly ahead, I think, in the magma problem. That's a suggestion.
I think it would be hard to know all the fluxes of magma in time. Are there any questions? You can unmute yourself, raise your hand, post something on the chat.
Could the students, could the students comment? What did that help you link your different coursework together? Was that helpful to you? Or this kind of presentation? If you could give me feedback, that's helpful for me too.
I think they're
terrified.
No, they are still wondering.
Cindy, I have a comment. I mean, does this mean that we need to be careful in interpreting GPS when it goes to, or is there? I mean, you're arguing that there is an alteration of the stress field at depth, right? And then
yes,
at the lower crust, then it seems like the lower crust is contributing. Is the density contrast plays a larger role, right?
Right, and when we start to intrude magma, I think it will be complicated to understand what the GPS is saying.
Right.
We need to, if we want to compare seismic and geodetic strain patterns, we have to be really cognizant of or consider the potential changes in state of stress with depth. And I think that Chris Scholes at Lamont has been telling people about this, about depth varying B value and depth varying state of stress for decades. And I tend to agree with him. Yeah.
Very good. Thanks.
Okay. So. So I think that we could end there because there is no more question.
Okay.
So I'm going to stop the recording.